in last class we have understood refraction. So, we talked about refractive index, we understood Snell's law. So, we talked about deviation of light, the amount by which it deviates when it comes across an interface of two different media. So, in today's class we will talk about the image formation because of diffraction. So, this is a phenomena which most of you would have observed. So, for example, if I consider a beaker with some water in it, right. So, let us say it is filled with water up to this much height, and if you are looking at it from the top. So, this is completely filled with water, and let us say there is an object which is placed at the bottom. So, there is one object. So, it could be anything, a small object at the bottom. So, when you observe that particular object from the top, so you all would have seen this and you know what will happen in this scenario. So, when this person sees that object, he sees that the object is slightly above its actual position, right. So, when you, this is something which you would have done also. When you look at the depth of the beaker from outside, it appears longer, but the moment you see it through the water, it appears to be having lesser depth, which basically means, so if let us say this height is some h. So, when you are looking it at from the top, this depth would seem little bit smaller. So, the beaker appears to be only this much deep, only this much deep. So, let us call it as h dash. So, this is a phenomena which most of you might have observed, and we can actually explain this idea today by using refraction and how image formation occurs during diffraction. So, what you can understand here is that, so if this object is here, you would actually observe that the image of this object will be formed over here. So, I have told you earlier also what an image means. Image basically is the perception of where you think the object is, right. It is your feeling that the object is at that position. It appears like the light is coming from that particular position. So, what happens is, when you see from here, the light which is actually originating from this blue object, by the time it reaches your eye, it makes you think that the light is actually coming from this black position, right. So, why that shift occurs and how much shift occurs is what we will be learning in this particular lecture. So, let us write it as image formation in plane surface refraction. So, whenever refraction occurs at a plane surface, which means a plane interface, you know the interface, right, the boundary between two different media. So, at that surface, whenever light strikes and refracts, so how image forms and where it forms is what we will be discussing about, clear. So, we will be learning this in two different cases. So, we will see the two cases. So, case 1 is where the light travels from a denser medium into a rarer medium, and case 2 would be from rarer medium into denser medium. So, these are the two cases which we will study now. So, let us consider an interface. You know one interface, right, it is the boundary between two different media. So, let us consider that those medium are having the refractive indices of mu 1 and mu 2. So, let us consider that those media are having a refractive index of mu 1 and mu 2, and in this case I will consider that the object is present over here. So, that is the position of the object. Let us say it is at a distance of some u. So, u is the object distance from the interface. So, remember, like in the earlier cases, in the case of mirror or in the case of plane mirror or spherical mirror, we measured all the distances from pole. So, in this particular scenario, we will be measuring all the distances from interface. So, if this is where the object is and the perpendicular distance from the interface is u, so that is what we call as object distance in this scenario. Okay. So, here let us consider that this is a denser medium. So, object is in the denser medium and this is the rarer medium. The observer is in the rarer medium. So, you can consider this to be air and water scenario, right. Air has a refractive index of 1 and water has a refractive index of 4 by 3 generally. So, this is a scenario where, so case 1 is basically mu 1 lesser than mu 2. Okay. So, now let us take two light rays from the object, which we usually do to locate the image of any scenario. We take two light rays from the object, we pass them, and by the time it reaches the eye of the person, so he analyzes where the light rays appear to come from, and that position is what we call as image. So, let us take two light rays. One usual light ray would be the normal incident light ray, so which would be this. So, let us consider that light ray is incident in this manner, the normal incidence case, and you all know that this light ray will just pass through without any deviation, right. So, normal incidence scenario, we have discussed this earlier. Now, let us consider one more light ray which goes like this. This is the incident light ray and it follows the laws of refraction, and you can easily say whether it bends away from the normal or towards the normal. It is moving from denser into rarer. So, rarer has lesser refractive index, lesser mu means higher theta. So, this light ray bends away from normal. So, this would be the final direction of refracted ray. So, these are the two refracted rays that the eye is receiving. Now, one important thing I will have to mention here. So, for all the cases which I am going to derive throughout this lecture, so this is something which is common. So, all this will be derived for normal viewing. So, normal viewing basically means that the person who is viewing the object, he is actually seeing it straight through in the vertically downward direction. So, as I have represented in the diagram, so he is not at some angle. So, if let us say there is a bucket of water here, I am not looking at it from this particular angle, I am looking at it from this angle. So, only for the vertical viewing scenario we will be deriving these cases, which means this light ray which I have drawn here, although I have drawn it little bit wider with a larger angle. So, these angles are considerably larger for you, right. So, remember that whatever diagram which you are seeing here is just for your understanding. I can't draw two light rays which are very close to each other and you can't see them basically. So, for you to see, I am just making them into a larger angle, but remember that these two light rays will reach the person's eye only if they are very close to the normal, clear, because he is viewing it from the top. So, for two light rays to reach the eye, they have to be very close to each other, remember. So, these angles, let us call this angle as I and this angle as R. So, I and R are very small angles. So, we will be deriving everything under this assumption only. So, keep that in mind. So, this basically means that the rays which we are considering are paraxial rays. Clear? So, there we took it as closer to the principal axis. In this case, paraxial rays are those which make very small angle with the normal incidence scenario or with the normal. Okay. So, if this angle is I here, so the one which I have represented, I can say that this angle here will also be equal to I, correct, and I have considered that the object is at a distance of u. So, now let us analyze what this person will see. Now, once again I am telling you, remember that these two light rays will reach the person's eye. Do not think that this light ray is going away, how will he see, right. So, that is just for representational purposes. Okay. So, these two light rays, when this person receives them, so he will just trace them back. Our eye only has the ability to trace the light rays which it receives and look for where the intersection point is. So, this light ray when traced back and this light ray when traced back, so they appear to meet at this particular position. It basically means that this person thinks the light rays which are coming through water are coming from here. So, this is where the light rays appear to originate from according to the person. So, but whereas there is nothing there. So, it is just the perception of the man that light rays are coming from this particular position. So, this is what we call as the image of this object, and let us consider this distance as V, and I will represent this distance as U, object distance and image distance. Okay. So, now we are going to find out the relation between u and v, just like we have done earlier for each and every scenario, relation between object distance and image distance. Okay. So, let us see. So, here we know that because refraction is taking place, I can apply Snell's law at this interface. You all know how to write Snell's law. So, the refractive index of this medium, which is mu 2 multiplied by sine of the angle with the normal in this medium, which is sin I, is equal to same in the second medium. So, here the refractive index is mu 1 and the angle it makes with the normal is r. So, into sin r, right. So, now if I use this assumption which we have considered, that the light rays which we are considering are paraxial rays, which makes I and r very small. You know that if angles are very small, if theta is very small, so we have used this assumption earlier also. If theta is very small, we can say that the value of theta will be approximately same as sin theta, which will once again be same as tan theta. We can make this approximation, right. So, what I will do is, instead of writing it as sin I, I will understand this sin I as tan I, because I and r are very small angles, clear. So, I will write this expression as mu 2 into tan I, right. So, tan I. So, this is I. So, if you look at this triangle, the bigger one, I will call this distance as some d. Now, tell me what is the value of tan I. So, tan I is opposite, which is d, by adjacent, which is u. So, d by u is equal to mu 1 into sin r, which is tan r. So, if you see here clearly, so this angle is r. Can I say this angle here will also be equal to r, because this is a vertical line, here the normal is a vertical line. So, these two are vertical lines and the refracted ray is just cutting them. So, whatever the angle it makes with the vertical here and the angle it makes with the vertical here should be same. So, this is r itself. So, now look at this smaller triangle which is formed over here. So, in this smaller triangle, what is the value of tan r? That would be d divided by the adjacent v. So, d by v. So, that is the expression which we get. So, if I cancel this out, I will be getting the final expression as mu 2 by mu 1, mu 2 by mu 1 is equal to u by v. So, that is the result which we have. Okay. So, let us not remember this result like this. I will tell you how to remember this result, a very simpler way and more effective way. For now, let us keep this derived result that way, and let us also do the derivation for the case 2. So, case 1 is when mu 1 is lesser than mu 2, which means light is travelling from denser medium into rarer medium. So, when it goes into rarer medium, the light ray bends away from normal, clear. Now, let us see a scenario where light ray enters into a denser medium coming from a rarer medium. So, we will do the derivation for that, and then by looking at both the results, let us generalize a formula, clear. So, case 2, and in case 2, I will draw a similar diagram, but this time I will consider mu 1 is greater than mu 2, right. So, final medium is greater than initial medium's refractive index. Okay. So, let me draw the ray diagram once again. So, mu 1, mu 2. So, this time this is the denser medium and this is the rarer medium. So, once again the object is, let us say, at this position, right. So, the object is here, same once again at a distance of u from the interface. Now, let us draw, the person is viewing it normally. Now, ray diagram. So, I will take two rays, one is the usual normal incidence scenario and the other one would be a light ray which is incident at some angle. So, this is the incident ray, the angle of incidence is I, right. Now, you know that when light enters into a denser medium, because mu is greater in the second medium, so this is greater, theta will be smaller. So, it bends towards the normal. So, it would be going like this, it bends slightly towards the normal. So, I can draw it like this. Clear? So, that would be the refracted ray. Now think about what the person perceives. What will the person think? He will receive this light ray and this light ray, and he will just trace them backwards. So, when this is traced backwards, it just extends further like this, and when this light ray is traced backwards, this goes something like this, and both the points intersect, both the lines intersect here, which means the light rays which are coming out of this surface. So, the light rays coming out of this surface onto the eye of the man, so they appear to come from this particular position. Clear? So, it is something like this. See, if the light rays are coming from here, are these two light rays which are actually going in this direction. It should have gone in this direction, but because of bending, so the light ray is bending like this. So, which means it appears to come from here. So, the person thinks that the light rays which he is receiving are coming from here. So, if this is the object, then this will be the image, right. So, V, right. Now, let us write the expression once again. So, in this case we can say this angle here will be R, and let me draw this diagram little bit clear. So, normal is the black line here. Okay. Now, in this case I can say that this angle is I, which means this angle will also be I. So, once again the same logic, these are two parallel lines, this normal line and this is also a normal line, and this light ray is cutting them. So, this angle and this angle will be same, and similarly we can say that this angle is R, this angle will also be R. The logic is same once again, two vertical lines, and this is the refracted ray which is cutting them both. So, R and R. So, same Snell's law once again. If I write Snell's law, I can write mu 1 into sin R is equal to mu 2 into sin I, and substituting the values, once again I will be getting mu 1 into sin R. Sin R you can write from looking at this bigger triangle. The value of sin R is this length, let us call this as d once again. So, d, you know that sin R can be taken as tan R, right. So, tan R is d divided by adjacent, which is v. So, d by v is equal to mu 2 times sin I. So, sin I will be writing it by using this angle, right, by using the smaller triangle here. Now, sin I or tan I is d divided by this length is u, right. So, d by u. So, dd will get cancelled, and simplifying this will give me mu 1 by mu 2 once again as v by u. So, if you observe, in both the cases we got the same result. So, or in this case, yeah, same result basically. So, mu 2 by mu 1 is u by v, and mu 1 by mu 2 is equal to v by u, both are one and the same. So, let us not remember it as mu 1 and mu 2, because they might change the numbers here. Instead of writing this as 1 and this as 2, if they write this as 2 and this as 1, if you write the same formula once again, then it would become wrong. So, the way we should remember this result is something like this: mu final by mu initial is equal to image distance by object distance. So, repeat it in yourself once again. I want you to not forget this ever. So, final medium's refractive index by initial medium's refractive index is equal to image distance by object distance. So, I want you to repeat once, twice, thrice, clear. So, final medium by initial medium, refractive index obviously, final by initial is equal to image distance by object distance, final by initial is equal to image distance by object distance. So, that is how we should understand this. So, whatever we have written here, you can see. So, if I convert this into image distance by object distance, I will be getting it as mu 1 by mu 2 is equal to v by u. So, see here, what is the final medium here? Final medium into which the light ray is entering is mu 1. So, we got mu 1 by mu 2 is equal to v by u. So, mu final by mu initial is equal to V by U. You can understand this in a different way also. Final medium is the one in which refracted ray is present. So, if I will write it here, final medium will have refracted ray and initial medium is the one which has incident ray. So, this is one way of understanding it, or you can also understand it in a slightly different way. You can understand this as the medium in which the object is present can be considered as initial medium, the medium in which the observer is can be considered as final medium. But I think this analysis or this way of remembering it would be more better, more effective also. So, just draw the ray diagram, look at where the light rays are originating and who is receiving the light rays. So, in each and every scenario which they give to you, first analyze who is the observer and what is the object. So, wherever the object is, draw light rays reaching the observer and then you will understand what is the initial medium and what is the final medium. Clear? I will repeat once again. So, in all the cases related to image formation for plane surface refraction, identify the object and identify the observer. Once you do that, finding out final medium and initial medium will be very simple. So, please once again remember this result, final medium by initial medium refractive index is equal to image distance by object distance. So, that is the idea. So, we will see some applications based on this. So, in some cases you will also be looking at the same relation which we have here. This expression can also be written in a slightly different manner, which I will write down here itself. So, mu final by mu initial is equal to, they will be writing it as apparent depth by real depth. So, this is another way of understanding it. The reason is pretty simple. You can see here. So, here the object is at an actual depth. If I consider this as air and water, so the object is at an actual depth of u, but the person perceives the depth of the object as this one, right. He thinks that this is where the light rays are coming from. So, whereas it is at an actual depth of u, it appears to the man to be at a depth of v. Clear? So, that is why we call the image distance as the apparent depth, apparent position. Clear? And u, the object distance, as the real depth at which the object is present. So, you can remember it like this also. So, whenever they are giving you the terms apparent depth and real depth, so do not get confused, they are just object distance and image distance. So, this is the final expression which we need to remember. Now, one very important point which we will have to keep in mind when it comes to plane surface refraction is that object and image will be on same side of interface. Same side of interface. So, in both the cases which we have drawn the ray diagrams for earlier, so you would have observed that. So, in whichever side the object is, the image also appears to be on the same side. So, this is a very, very important result which you will have to keep in mind. So, let us solve one simple scenario here. So, let us consider the earlier case which we have taken, the case where we have a beaker with water. So, this is water and there is a object at the bottom, let us say a coin, and there is a person who is viewing it from the vertical, and you all know that the refractive index of water is 4/3. Let us consider the depth of this to be some 12 centimeters. Now, what is the apparent depth? Find the apparent depth as seen by observer. So, I will directly apply the formula. So, please observe carefully how I am substituting the values. I will first write the expression mu final by mu initial is equal to image distance by object distance. Clear? So, this is the observer. In this case, it is pretty simple. This is the observer and this is the object. So, light rays start from here and travel this way. So, you can say that this is air, so which has a refractive index of 1. So, light travels from denser to rarer. So, final medium is air here. So, final medium's refractive index will be 1 divided by initial medium's refractive index. This is where the light rays are originating from. Incident rays will be in this medium, refracted rays will be in this medium, right. So, initial medium's refractive index will be 4 by 3 is equal to, so we can say that the image distance is nothing but the apparent depth divided by u. Object distance will be the real depth, which is 12 centimeters in this case. So, if I simplify this, what do we get? So, I will get apparent depth is equal to 12 into 3 by 4, right, 12 into 3 by 4, which is 9 centimeters. So, that is the idea basically, clear. So, a simple case, that one. So, let us see one more similar scenario. So, this time we will once again consider that this is a lake, right. So, a lake, and here there is a fish, okay. So, this is a fish and let us say here there is a bird. So, this is the bird, okay. So, bird watches the fish and fish also watches the bird. In this case, we are going to do two scenarios. So, one scenario in which bird is the observer, fish is the object, and in the second scenario where fish is the observer and bird is the object. Let us consider once again, this is air having refractive index of 1, this is water having refractive index of 4 by 3, and let us take some depths. So, let us say this is 6 meters and this length is some 12 meters. So, let us consider a scenario like this, right. Now, let us find out the first case, case 1. Apparent distance of fish as seen by bird. So, what is the apparent distance at which the fish appears to be according to bird? So, bird is seen. So, this is the bird, right, it is flying. So, it is so we need to find out the distance at which the fish appears to be according to the bird. So, in this case we know that fish is the object, from which the light rays are coming out, and those light rays are received by bird. So, I will directly apply the formula. I am not going to draw the ray diagram every time. So, in this case I can directly say final medium's refractive index, okay, let me write the expression, mu f by mu I is equal to v by u. So, substituting final medium's refractive index, clear, the fish, from the fish the light rays are coming and reaching the bird. So, this is the final medium, this is the initial medium. So, final medium is 1 divided by initial medium is 4 by 3 is equal to v by u. So, we have considered that, okay, v is, let me write it as v itself divided by u. The object, which is fish, is at a depth of 6 meters. So, 6 meters. So, I will be getting the expression as v is equal to 6 into 3 by 4, which is 18 by 4, which is 9 by 2 meters. So, it means that although the fish is here, for the bird the fish appears to be at a distance of 9 by 2 beneath the water. Remember, all these distances are measured from the interface, which means as the fish is at this position, the image of fish. So when the bird sees the fish, so the fish appears to be at a distance of 9 by 2 meters according to the bird from the interface, but they are asking us the apparent distance of fish as seen by bird. So from the bird, at what distance is the fish appearing to be? So which means, so this image of fish is at what distance from the bird, and how much would that be? 12 plus the further distance from interface, which is 9 by 2. So apparent distance in this case will be 12 plus 9 by 2, 24 plus 9, which is 33 by 2 meters. So that is the distance of fish as seen by bird. Now let us solve for case 2. So in case 2, fish is observing the bird. So this time everything changes. So this time bird is the object. So light rays start from the bird and reach the fish. Or I'll draw a different diagram. So this time the bird is here. So the fish is here. Okay. So this bird, the light rays start from the bird and travel in this direction to reach the fish. Clear? So once again keep in mind, in each and every question think about which is the initial medium and which is the final medium. So I'll write the values expression directly. So mu final by mu initial. So case 2 this is. So mu final by mu initial is equal to V by U. So substituting the values, final medium is this, light ray is coming from the bird and reaching the fish. So this is initial, this is final. So final is 4 by 3 divided by initial is 1 is equal to V by U. What is the value of U? What is the distance at which the bird is, which is the object, from the interface? So from the interface, the object is at a distance of 12 meters. So into 12 meters. So solving this will give me the value of V as 12 into 4 by 3. So 4 into 4, 16 meters. Remember once again, this is not the final answer, because that is the distance of the bird as seen by the fish from the interface. So which means that is the image distance of the fish. So if this is the bird, so the image of bird will be here. So this is where the image appears to be, and you all know why it moves away, right? Because the light ray which comes from here bends towards the normal and it appears to come from a larger distance, right? So that is the idea. So from here the image of bird is at distance of 16, which means from fish the apparent distance in this case will be 16 plus further 6 meters. So 16 plus 6, which is 22 meters. So that is the idea. So it is a very simple application. So as long as you substitute the values and remember the formula correctly, so you can easily solve such cases. So mu final by mu initial is image distance by object distance. Students, now we will see one more question. So this is a case of multiple refractions. So you all know how we deal with cases where there are multiple scenarios happening. So we have done in the case of mirrors. So if we take a plane mirror and a concave mirror, or any two kinds of mirrors, whatever is the image formed by one mirror will act as the object for the other, right? So because light reflecting from here will appear to come from the image of this, and this will be the object for the next one. Clear? So this is a case similar to that. Whenever successive reflections or refractions are happening, so you will take the image of one as the object for the other. So, okay. So let us consider a scenario like this. So where we have the bird and the fish once again. So fish is in water. So this is water having a refractive index of 4 by 3, and let us consider that this whole medium in between, which looks like a slab. So this whole thing here is a glass slab, transparent glass slab, and the refractive index of glass is 3 by 2, and here this is air. So, a hypothetical scenario, right. So, the mu value for air is 1. So, let us take some distances, 6 meters let us say, and this is 9 meters and this is 12 meters. Let us consider a scenario like this. Now, just like the earlier case, so we have bird and we have the fish. So, let us not do two cases once again, let us solve for any one of the case. You can try the other case on your own. So, what I will do is I will solve for image of bird as seen by fish. I will write it down here. I am solving for image of bird as seen by fish. So, fish is the observer, bird is the object. So, let us solve for that scenario. So, remember, as the light starts from the object which is the bird and travels to the fish which is the observer, it has to undergo refractions at two different surfaces. So, refraction occurs at this surface and refraction occurs at this surface. So, which means, think of it like this. So, as light is traveling from here, so let us say two rays of light have travelled from here and entered into this medium. So, as light enters into this medium, so the two light rays in this medium, will they appear to come from the bird? No, they appear to come from the image of bird, clear. So, what that means is that once refraction has occurred at this surface, the two light rays which strike the second surface, the two light rays will appear to come from not the bird, but the image of bird, right. So, that is what I told you earlier, whatever is the image formed by this refraction at this surface will act as the object for this surface and will continue the same process once again. So, let us do that. So, first let us write the refraction at this surface, light is travelling in this direction. So, first refraction occurs here. So, this is what I am writing the equation for. So, let me call it as first refraction. Okay. So, first refraction. So, general formula, final medium by initial medium is equal to V by U. So, final is this 3 by 2, I will write it down directly. So, 3 by 2 divided by initial medium is 1 is equal to image distance, let me write it as V by U, U is 12. So, 12. So, that is it. So, when I simplify this, I will get the value of V as 18 meters. So, which means the light which is entering into this medium, you can consider two light rays. So, one light ray is this normal ray, and if you consider one more light ray like this, so it bends slightly inwards and this light ray appears to come from somewhere over here which is at 18 meters from this interface. So, now these two light rays strike this surface, this light ray and this light ray. Where do they appear to come from? They appear to come from a point which is at a distance of 18 meters from this surface, which means what is the object distance for the second surface? Let me write that down. So, refraction, second refraction. First, let us write the object distance for second refraction. So, tell me what is the object distance for second refraction? So, light rays are coming from here. So, this length is 18 which we have just calculated plus 9, 18 plus 9 is 27 meters. So, 27 meters, right. Now, refraction occurs at this surface and this light ray will once again bend either towards the normal or away from the normal depending on you know the case, rarer to denser or denser to rarer. Okay. So, once again I will write final by initial is equal to V by U. So, now light ray is entering from this medium into this medium, final is water. So, 4 by 3 divided by initial is this 3 by 2 is equal to V by object distance. Object distance is 27 meters. So, 27 meters. So, substituting and calculating, I will be getting V is equal to 27 into 8 by 9, 8 by 9. So, solving this will give me 24 meters. So, which means the image of bird as seen by fish will be at 24 meters from this interface. So, from here the bird appears to be at 24 meters, which means from the fish it will be at a distance of, so distance as seen by fish is equal to, you can now easily tell that. So, from this interface the bird's image appears to be at 24, which means from here plus 6. So, 24 plus 6, which is 30 meters. So, that should be the answer. So, you can solve for the other case. In this case, in this scenario, you can find out what is the distance at which the fish appears as seen by the bird. So, you can try that scenario, right. So, students, we have seen multiple refractions happening successively one after the other. So, now let us combine reflection and refraction, both simultaneously happening. So, we will include both the concepts now. So, to understand, let us consider an example. So, let us consider that this is a slab of glass, so a glass slab which is silvered on one side. So, which means this surface will act as a mirror. So, if light falls on that, it gets reflected back. So, this is glass. So, you know the refractive index would be 3/2, and let us say there is an object which is placed here. So, an object is placed here, O. So, let us take distances to be, so let us say this distance is some 10 centimeters and this distance is 15 centimeters. Now, we need to find out the final location of image of this object. So, if the object is here, where is the final image of that form? So, according to a person who is viewing from here. So, a person is viewing from here. So, according to him, where is the final image of the object? Now, keep in mind, he is not looking at the object directly, we need to look at the image of this which is coming back after reflection, which means the light rays should first pass through this surface, refract from this surface, then strike the mirror, reflect from the mirror, and on the way back they should once again pass through this surface, refract from this surface, and then reach the person's eye. Clear? So, that is how he is seeing the final light rays. So, you should follow the light ray. So, you go with the light ray, you think of what the light ray is experiencing, what is the path of the light ray, and write equations for each and every scenario that the light ray comes across. So, first light ray from here it goes and enters into this medium, it refracts into this medium. Let us also understand this through a ray diagram. We will also write equations and we will also simultaneously draw the ray diagram adjacent. Okay. So, one light ray, or I do not think we need to write this light ray each and every time. So, I will directly draw it first itself. Clear? Okay. So, this light ray will just go, reflect and come back. So, let us follow the other light ray. So, if I consider another light ray, so let us say this light ray is like this. So, the normal would be like this, because it is entering into a denser medium, we can say that it bends slightly towards the normal and it appears to come from a slightly farther distance, right. Okay. So, first let us write the expression for refraction here. We know that there are two refractions and one reflection occurring, correct. So, first refraction, let me write the order first. First will be refraction, that is what is happening. Second is reflection, and third, on the way back it is once again refracting. Okay. So, for the person to see, remember that for the person to receive the light rays have to undergo all those three and then reach the person's eye. Clear? He is not looking at the object directly. So, think that there is an opaque substance which is placed here blocking the view of the object. So, the light rays can only go through that and then reflect and reach the person's eye. Okay. So, let us write the equation for first refraction. So, here, so anyways it is a plane surface, so I can directly write final by initial is equal to V by U. So, final is 3/2 by 1 is equal to V we need to find out, let us call it as V dash, because that will act as the object for the next reflection, clear, we will call it as V dash. So, V dash by, what is the object distance here, we have taken it as 10, so by 10. So, simplifying this will give me V dash is equal to 10 into 3 by 2, which is 15 centimeters. So, which means this point from which the light rays appear to come from. So, the mirror thinks that the two light rays which it is receiving, which are these two light rays, this is one light ray which it receives and the other one would be this. So, these two light rays which it is receiving will appear to come from here, right. So, this is the object for the mirror. Now, what is the object distance for the mirror? 15 plus, we have already calculated this length as 15 once again. So, whatever is this value we calculated here is from the interface, we already know that. So, 15 plus 15, which is 30 centimeters. So, let me write that down. So, for the second case, second interaction, object distance is 30 centimeters, right. Okay. Now, you know that what happens with this light ray. So, this light ray will get reflected from here. So, if I draw a normal and make the reflection, so the light ray gets reflected from here and once again comes on to this surface, clear. So, this is one light ray and one more light ray will be coming like this. So, these are the two light rays which reach the mirror, and after reflection these are the two light rays which are coming back from the mirror. Now, you can easily say where the two light rays appear to come from. The two light rays appear to come from behind the mirror. You already know at what distance it will be. Whatever is the object distance for the mirror, same will be the image distance for the mirror. So, image distance in this case will be once again 30 centimeters behind mirror. Now, you know that this point, what will that point be? That is the image formed in the mirror, which will also be the object for this interface, correct. So, the light rays which are striking this surface, you can see these two light rays, they appear to come from here. So, let us write the third interaction. So, third interaction is once again refraction. So, let us first write down the object distance for that. So, object distance is equal to, so for this surface, this is the object. So, at what distance is it? 15 plus 30. So, 15 plus 30 is 45 centimeters, right. So, now you know once again that these light rays after refraction from this surface over here, they bend away from the normal and they eventually appear to come from somewhere over here. So, that is what happens. So, this person receives this light ray and thinks that the image of this object is here. So, let us find out that distance eventually. So, this length is 45, the object distance for this surface. I will write the refraction formula for this surface, final medium by initial medium V by U. So, final medium is 1 by initial medium's refractive index. This is the initial medium. So, 3 by 2 is equal to final image distance. So, let us say this is the final image distance, we will call it as V. So, V by object distance for this surface would be 45. So, that is it. So, simplifying this will give me 45 into 2 by 3. So, 45 into 2 by 3 and this is 30 centimeters. So, I have not represented that in the diagram correctly, but because I have taken a very large deviation. So, the deviation will not be this much. By looking at the result, you can understand that there will be slight deviation and this light ray appears to come from here, 30 centimeters from here. So, from here it will be at 30 centimeters. So, you can write that down. So, final image is formed at, So, from here if it is 30, this is 15, which means from the mirror it is at 15. So, it is formed at 15 centimeters behind the mirror. So, that would be the answer for this case. Okay. So, we will see one more scenario like this. Students, we will see one more question similar to the earlier scenario. So, this is the same case which we have taken earlier. So, this time this surface which we have earlier taken to be behaving like a plane mirror, let us consider that this time it behaves like a convex mirror. So, the glass medium is something like this and we are just silvering this surface. So, the distance is same from the pole, it is at a distance of 15, the interface plane interface is at a distance of 15 from the pole and object is at a distance of 10 centimeters. Okay. So, let us consider that the focal length of this convex mirror is some 60 centimeters. So, let us consider a scenario like this and let us do the same analysis, right. The idea is the same once again, a person is observing from here and he needs to find out where the image is formed. So, everything will remain the same, the method is still the same, the only thing is that this time we will be using mirror formula for this. So, first refraction should occur through this surface, then that will act as the object for the convex mirror will form an image that will act as the object for this surface while coming back, clear. So, let us do that. So, the first interaction we already know, we have already done that also, I will quickly write it down. Final medium which is 3 by 2, this is 3 by 2. So, 3 by 2 by 1. So, 3 by 2 by 1 is equal to image distance by object distance. Image distance is let us say V dash by 10. So, solving this gives V dash as 15 centimeters. So, this part we have already done. Now, the second interaction is with the convex mirror. Now, the light rays which are coming, we know that they are coming from 15 centimeters, which is this. So, which means the light rays which are striking the convex mirror, they appear to come from here, because the light ray which travels from here bends slightly and strikes the convex mirror, appearing to come from here. So, this is how the ray diagram would be. Okay. Now, what is the object distance for convex mirror? Object distance is equal to, how much is that? 15 plus another 15. So, we can say 30. But remember, I have just written the magnitude here. You know that while substituting in mirror formula, we should use sign convention. So, this is the convex mirror. So, let me write mirror formula first. 1 by u plus 1 by v is equal to 1 by f. So, u, we know that light ray is travelling like this. So, all distances in this direction are positive, whereas the object is this side from the pole. So, we should be taking it as negative u. So, how much is that? Minus 30. So, minus 30 plus 1 by v is equal to 1 by f. F for convex mirror is positive and it is given as 60. So, 1 by 60. So, solving this will give me the value of v as 1 by 30 plus 1 by 60. If you take the reverse, you will be getting 60 into 30 by 60 plus 30, which is 90. So, 3 is 20. So, you will be getting v is equal to plus 20 centimeters. And you know what positive sign indicates there? Positive sign indicates that the image is formed behind the mirror. So, let us say it is formed over here. So, this length will be 20 centimeters, which means the light rays which are going to get reflected from here like this, they appear to come from this position. And these light rays will once again strike the interface, plane surface, undergo refraction. So, I have drawn the diagram little bit wider. So, if the rays are taken closer, then you can easily see it. So, you can draw a normal once again here, and it is entering into the rarer medium. So, the light ray bends away from the normal and eventually the final image will be formed somewhere over here, clear. So, let us write the expression now for the third interaction. Third interaction is once again the plane surface refraction. Now, if you look at the light rays which are coming from the mirror and striking the surface, so from the mirror and striking the surface, so from where do these light rays appear to come from? 20, 15, 35, clear? So, the object distance for this interface, I will write it down, object distance is equal to 35 centimeters, right. So, once again please observe carefully. So, this is the interface I am talking about and this is the incident light ray onto this interface. So, look at where that incident light ray is coming from. So, light ray is coming like this, where does it appear to come from? Here. So, this is 20 which we calculated and this is 15. So, object distance will be 35. So, let me write the refraction formula for this surface, for this interface. So, let us, if I write it, final medium is 1, initial medium is 3 by 2. So, 1 by 3 by 2 is equal to final image distance is V by object distance is how much? From here to here we took it as 35. So, that is it. So, finally solving this will give me the value of V and that would be 35 into 2 by 3, right. 35 into 2 by 3 will be 70 by 3 centimeters. So, that is where the image will be formed. Now, let me ask you one thing, 70 by 3 centimeters from this interface, will it be on this side or that side? It will be on that side and the reason is because the object for this is this one. So, I have told you earlier, whichever side the object is, image due to plane surface refraction will also be on the same side. So, the final image appears to be here at a distance of 70 by 3 centimeters, clear. So, that should be the answer. By looking at the diagram, I have drawn this as 15, but this 70 by 3 is greater than 15, that is because I have taken a larger deviation. So, do not worry about that. So, just understand how to simplify the scenario. So, that is the idea finally, right. So, students, that is about the image formation, locating the image and understanding what distance it is present, which side it is present. So, we have seen all that. So, let us now talk about another scenario in which we will be considering a glass slab and looking through the glass slab. So, let us say we have a glass slab like this. So, let us say the thickness of this slab is T and there is an object over here. Let us say the object is at a distance of u and there is an observer over here. Now, so the light rays coming from the object pass through the glass slab, undergoes two refractions, one at this surface, one at this surface and then reach the person's eye. So, we are now concerned about the final image, the final location of the image as seen by observer. So, we know this, we know how to write the refraction at the first surface, refraction at the second surface, find the location of the image. So, we will derive that and we will have one particular result. So, what happens here is that if let us say the final image is formed somewhere over here or here. So, the person thinks that the final light rays are coming from let us say somewhere over here, the location of the object is shifted by some distance. That is what the observer perceives, which means the person thinks that the location of image has been shifted by some distance because of the presence of this glass slab. So, the glass slab, what kind of effect is it creating here? It shifts the location of the image. So, that is what it does. So, what I am going to do here is I am going to write it as shift produced by a glass slab. So, basically I am going to find out the final location of the image itself and find the difference in the distance between the object and the image locations, clear. So, that is the distance by which it was shifted by as seen by the person. Okay. So, we know the method, we will draw the ray diagram first. So, let us consider some refractive index. This is mu 1, this is mu 2 and this is mu 1, right. So, mu 2 is the refractive index of the slab. Let us do for a general scenario, let us not consider it as glass in air, let us do it as a medium having a refractive index mu 2 in a surrounding of refractive index mu 1. So, if you need to consider for a slab placed in a, substitute 1 and 3 by 2. So, a general scenario is better, right. Okay. So, let us take a light ray. I will draw the ray diagram in this scenario by considering that mu 2 is greater than mu 1. I will consider this as denser medium, mu 2 greater than mu 1 for the derivation, clear. So, the light ray bends slightly towards the normal because this is the denser medium, which means the light ray appears to come from a farther point, right. So, if this is u, how much will this distance be? You know how to calculate. So, I will write the equation here. First, refraction. So, for first refraction, if I write final medium into which the light ray is entering is mu 2, initial medium is mu 1. So, I can write mu 2 by mu 1 is equal to V dash by, I am writing V dash because that is not the final image, right. So, V dash by u. So, solving this will give me V dash is equal to mu 2 u by mu 1, clear, mu 2 u by mu 1. Okay. So, I have known this distance now, mu 2 times u by mu 1. Okay. Now, this light ray strikes the second surface. Now, look at the second surface, the light which the second surface is receiving, one would be this normal light and the other one would be this, and these two light rays appear to come from here, from this distance. But what is the object distance for the second surface? Let me first write the object distance before substituting. So, for the second refraction, I can write object distance. Object distance is equal to, how much will that be from here? At what distance does the light ray appear to come from? T plus this length, clear. So, I will write that here. So, that would be mu 2 u by mu 1 plus T. So, that is the object distance for second surface. Now, let us write the refraction formula for second surface. So, now the light enters, strikes here. So, the normal would be something like this and it bends away from normal. So, you can see here. So, this is the initial direction of light ray. So, it is moving in this direction, it is slightly bent this way, appears to come from here and then once again bends this way and goes out. So, the person who is receiving these two light rays, one is this and the other is this, he will just trace these two light rays backwards and he thinks that the light rays are coming from here, they are originating from here. So, when I extend these two light rays backwards, so this light ray, if I extend it backwards, so this and this will be intersecting here. So, which means this is the final location where the image is formed for this object as seen by the person. So, we are going to find out that distance now. So, let us write the formula for this. Final medium mu 1, initial medium mu 2. So, final medium by initial medium is equal to object distance. We already wrote that. So, mu 2 u by mu 1 plus T into V. I will write it as V, the final image. So, I will need to find the value of V now. So, which implies that V is equal to, just cross multiply. So, mu 1 by mu 2 into this. So, this will get cancelled, you will be left with u plus T into this. So, you will get u plus T into mu 1 by mu 2, mu 1 by mu 2. So, that will be the final expression which we will be getting for object image distance. And remember once again, this is the distance at which the image is formed from the second surface, Clear? We wrote the equation for second surface. Now, what do we need to find? What are we concerned here about? Shift produced by glass slab. So, we can say that shift is nothing but this length, the distance between the object and image. Object and image. So, to find out that distance, so please observe carefully. We know the distance at which image is present from this surface. So, I know this length, which is what we have calculated earlier as V. Clear? So, I will call this distance shift as S, right. Now, can I write shift plus V is equal to U plus T, thickness of the slab, plus object distance is nothing but the distance between object and the second surface. That is also equal to this image to second surface length plus image to object length. So, that is what I will write. So, shift is equal to U plus T minus V. Clear? U plus T is the whole length. So, from this if I subtract V, I get S. So, U plus T minus V. V I already know as U by mu 2. So, this is U plus T minus V. Okay. So, just calculate that U is getting cancelled here. Now, that is a very important observation which you will have to make, which I will tell you in a while also. So, let me take T common here. So, if I take T common, I can write it as T into 1 minus mu 1 by mu 2. So, this is the final formula which we get for shift. So, this is sometimes also written in this way. It can also be written as T into 1 minus 1 by mu 2 1, which means the refractive index of the slab with respect to surroundings. You all know how, you all know this representation, right. So, I am basically writing this mu 1 by mu 2 as 1 by mu 2 by mu 1, and we all know what mu 2 by mu 1 is. Mu 2 by mu 1 means mu 2 1, refractive index of 2 with respect to 1. So, that is the final expression which we get. Now, there are few important things which you will have to keep in mind here. The final expression for shift, if you observe, there is no term U. U is not there in the shift, right. We have just cancelled out the U just now. So, which means shift produced does not depend on the object distance. So, wherever you place the object, so whether you place the object here or here or here, so as long as that person is observing through this glass slab, so he is keeping the glass slab in front of him and observing an object behind that slab, that object will always appear to shift from its position by this much value or this much value. So, that is what this means. So, the shift that occurs in the location of the object has nothing to do with what distance it is present from the slab. So, an object which is placed very close to the slab and an object which is placed very far away from the slab, both will appear to be shifted by the same distance according to the man. Clear? And that is T into 1 minus 1 by mu. Now, there is one more very important thing here. Remember, in this particular case, if you see, I have considered mu 2 greater than mu 1, right, which means the slab has a higher refractive index than the surrounding. Now, when the slab has a higher refractive index, the location of the object appears to shift towards the observer, right. Object appears to shift towards in this direction. So, if you can observe here, if mu 2 is greater than mu 1, then in this particular case, if mu 2 is greater, this value will be lesser than 1, which means this whole value will be a positive term. If this whole value is positive, the overall shift is positive. So, here we can understand it like this: shift is positive implies it occurs in the direction of incident ray. Now this is a very very important thing, please keep in mind. So I will also write the opposite of this. So we get a negative value of shift. When you calculate this, if you are getting a negative value, that implies that the shift occurs in the opposite direction, of incident ray. So we have not drawn the ray diagram for that. If you want, we will draw in a while, or otherwise you can try it on your own also. So what I have drawn here is the ray diagram for a case where mu2 is greater than mu1, and when mu2 is greater than mu1, when the slab has higher refractive index, the object's position appears to be shifted in the direction of light ray. So light ray is travelling in this direction. So incident rays are in this direction. So the shift also occurs in the same direction if you get a positive value. And when do you get a positive value? When mu2 is greater than mu1, when slab has higher refractive index. So if you want, you can write that also here. So when do we get this scenario? So we get this scenario if slab has higher refractive index than surroundings. I hope this is clear. So you can automatically understand for the second case also. When do we get a negative shift? You can see clearly. When will this be negative? When will this term become negative? For this term to be negative, because this is 1 minus mu1 by mu2, so this should be greater than 1. When will that be greater than 1? When mu1 is greater than mu2. So that is this case. So in this case, you will be getting a negative shift if mu1 is greater than mu2. Mu1 means surroundings are having higher refractive index than the slab. Is that clear? So that is the basic idea. So there are few important points you will have to keep in mind here, which I have noted down over here. So please note them down clearly. These are very very important points regarding shift produced, right. I will just summarize that once. The first thing is that the shift produced does not depend on the object distance from the slab. So whatever distance the object is present, each and every object will be shifted by the same distance. Now the magnitude of that shift depends on the refractive indices and the thickness. Now and also the direction in which the shift occurs, whether the direction of shift is in the direction of incident ray or the opposite direction of incident ray, is decided by whose refractive index is higher. If the slab's refractive index is higher, in the direction of light ray. If the surroundings refractive index is higher, opposite to the direction of light ray. So just keep this in mind, T into 1 minus 1 by this is relative refractive index of slab with respect to surroundings. Maybe I will write that down. This mu21 represents relative refractive index of slab with respect to surroundings. So that is the idea. So students, let us see one more question based on the shift produced by a glass slab. So you have a case like this, not a glass slab, any slab placed in a surroundings. So here the surroundings is air. So here we have a slab whose refractive index is unknown and a concave mirror object is placed. So the distances are given. Thickness of the slab is 8 centimeters, object is at 5 centimeters in front of slab. Distance between slab and the pole of the mirror is 21 centimeters. Now look at the question. Find mu of slab such that image and object coincide with each other. Okay. So you know this already. So, I have told you earlier also, whenever you look at this thing, image and object coincide with each other, the first thing that should come to your mind is that somewhere in this process of light traveling forward and coming back, definitely the light ray is striking a surface perpendicularly. So, only when a normal incidence occurs, the light ray will retrace its path and come back to the source. I hope you remember the method which we have discussed earlier, retraceability, right. So, that is the idea. So, which means you know how the path of the light ray would be here. The light ray strikes this surface, slightly bends, because this is A, this is definitely a higher refractive index. So, it bends slightly and once again bends away from the normal and it travels like this and it goes and strikes the mirror. Now, for that to retrace its path, definitely this surface, this light ray which is striking the mirror should strike it normally, and you all know when that happens. It will happen if this light ray appears to come from a point which is, what is it? That would be the center of curvature. So, if this point from which the light ray finally appears to come from before striking the mirror, if this point behaves like the center of curvature of the concave mirror, then this light ray will retrace back, same path it will follow and it will return back to the object and image will be formed there itself. So, that is the basic idea. So, look at the distances given here, 5 centimeter, 8 centimeter, 21 centimeter. So, what is the total distance between the object and the pole? How much is it? So, 5 plus 8 is 13, 13 plus 21 is 34. So, 34 centimeters is the distance between object and the pole of concave mirror. But we know that the final light ray which is coming out of the slab should appear to come from here, and you all know this should be the center. If this is the center, what is the distance between center and pole? We know that OP is 34 centimeters from the question given to us. Now, we also know that CP should be equal to how much, because that is the radius of curvature. Focal length is given as 15 centimeter. We can say that CP is equal to 30 centimeters, which is the radius of curvature of the mirror. So, object will coincide with image if the final point from which the light ray appears to come from is the center of curvature. So, that is the basic idea. So, I am not going to write the equations for each and every interaction here. What I know here is that I know the property of this glass slab. The glass slab will take the light rays and it will send on to the other side. The only thing it does in that process is shift the location of the object. So, if the light rays are actually coming from here, by the time the light rays go to the other side, the light rays will appear to come from a point which is shifted by some distance, and we all know that shift value. The value of that shift is T into 1 minus 1 by mu of slab with respect to surroundings, correct. So, I will directly use that expression, I do not have to write the equations once again. So, what is this distance by which the shift should occur? You know the lengths already, OP is 34. So, the object from the pole is at 34 centimeters, center from the pole is at 30 centimeters. So, what is the distance between center and the object? That is 4 centimeters. So, it means that this center, which is also the image produced by this glass slab. So, the light ray which is coming from the glass slab is coming from here, right. So, this is where the image is produced by the glass slab, this is the shift produced by the glass slab. So, that should be equal to 4 centimeters. So, that is the final result which we will be solving for. We know the thickness of the slab already, 8 centimeters. So, 8 centimeters into 1 minus 1 by refractive index of slab with respect to surroundings, means refractive index of slab by refractive index of surrounding, which is anyways 1. So, I am not writing that, is equal to 4 centimeters. So, simplify that, what do we get? I will be getting 1 minus 1 by mu slab is equal to 4 by 8, which is 1 by 2. Yeah. So, solving this I will get mu slab is equal to 2. So, that should be the answer for this. So, see how simpler it becomes if we analyze this correctly, if I understand this meaning correctly. So, it is a very simple scenario. All we will have to do is, all we will have to understand is the light which is striking the mirror should appear to come from center of curvature, and the light which is striking the mirror has already been shifted from its position by t into 1 minus 1 by mu relative. That is the idea.